In this video, I'll give you a brief intro into the vast and incredibly interesting field of graph theory. Here's an example of a type of graph that we're going to talk about extensively in this video. What's the simplest definition of a graph? Graph as a network that helps define and visualize relationships between various components. These ideas, of course, have more formal names in graph theory. In this example, the circles that you see represent the components, and the lines connecting them can be thought of as signifying a relationship between the components. These ideas, of course, have more formal names in graph theory. We refer to these circles as vertices or nodes, and the relationships signified by connecting lines represent what we call edges in a graph. Let's first start with the most important question. Why should we care about graph theory? And the short answer to this is graphs show up everywhere, sometimes in expected ways, and also sometimes in surprising ways. One of the most direct applications are mapping and navigation applications. In any of these applications, you often deal with roads and intersections, which can be naturally modeled as a graph, where each vertex represents an intersection, and the edge between vertices signify the roads between intersections. You could imagine navigation applications might be interested in the best route between a starting point and an ending point, and this problem naturally translates into many well-known graph theory problems. Let's now proceed to formally define a graph. A graph is a set of vertices and edges, where each edge is a connection between vertices. The way we usually denote an edge in a graph is by referring to it as a pair of vertices. As mentioned before, vertices and nodes are just different names for the same concept that we will use interchangeably when discussing graphs. If you're forced to mathematically write down a definition of a graph, we can use set notation. For this particular graph, the vertex set looks like V, and our set of edges would be denoted as E. Let's now transition to the types of graphs that you may encounter. The main graph we've seen so far is specifically called an undirected graph, where, for example, if I have an edge connecting vertex 0 to vertex 1, it's implied that I also have an edge from vertex 1 to vertex 0. A graph where this would not be the case is called a directed graph, where now edges are unidirectional. Directed graphs also have their own classes. This particular graph has a cycle, so we can be more specific by referring to this graph as a directed cyclic graph. On the other hand, if a graph is directed and contains no cycles, we refer to that specifically as a directed acyclic graph, which is a specific subset of graphs that has been studied quite rigorously since they show up in all sorts of interesting problems. Another important graph is a weighted graph. This graph is unique because each edge now is not treated equally, and some edges might have a larger weight than others. This can naturally model interesting metrics like traffic, distances on maps, and many other ideas. Another important class of graphs is trees. Trees have three key properties. All trees are connected and acyclic. Removing an edge from a tree will disconnect the entire graph. And furthermore, adding any single edge to a tree will create a cycle. These are three valid examples of trees, and I encourage you to take a second, pause the video, and confirm that these properties hold. Personally, I find verifying the second and third properties surprisingly satisfying. It really emphasizes how fragile a tree structure is, which I think is kind of cool.